Okay, so today's video, I'm going to continue this Wallis product as what I've actually done so in our first part of the video. So today is part 2, and here we go. Okay, so today, in the last video, I actually proved, the series for pi over 2. Today, we are going to look at 3 more Wallis product. Okay, so namely, the first one you can see is 2 pi over 3 root of 3. Okay, we can see that from the numerators, they are multiples of 3. Okay, all the way to infinity. Likewise, denominator, in this case, you have a 2 to the 4, 5, 7, 8, 10, etc. So they are consecutive natural numbers, okay, in this case. Now, in the second equation, you can see is pi over 2 root of 2. Namely, same thing, the numerators, they are 4, 8, 12. Okay, in other words, multiples of 4. Whereas denominators, they are 3, 5, 7, 9, 11, 13, consecutively, etc. to infinity. Okay, and the third Wallis product, you have basically your pi over 3, and numerators will have multiples of 6. Denominators, you have consecutive numbers starting from 5. 5, 7, 11, 13, 17, 19, etc., etc. So today is to show how these products, these infinite products, is going to converge in these 3 numbers. Okay, namely they are involving pi. Okay, so I'm going to show the first one. Okay, just a recaps. Okay, this is the Weierstrass expansion for the function of sine x over x. Okay, so this is just what I brought forth from our first part of the video. So in this second part, will be more straightforward. I will just bring out the multiples. So in this case, the Weierstrass factorization theorem, as you can see on the right hand side, you have 1 minus x squared over pi squared, etc., etc. So over here, this is actually what we call the remainder, for the sorry, not remainder, the roots. Okay, so these are all the respective roots for sine x over x. Okay, so for the first one, I'm now going to take for x is equals to pi over 3. So what happens when x is equals to pi over 3? So for pi over 3, if I'm going to substitute them in the left hand side, you have sine pi over 3 over pi over 3. Okay, and on the right hand side, I replace all the x with pi over 3. So, this is what we are doing. Okay, so that's the first part. Now, on the left hand side, if I'm going to evaluate this part, I have 3 root of 3 over 2 pi. Okay, I hope you can see what's going on here. All right, so now on the right hand side, if I'm going to evaluate all these respective terms, I can break it down because pi's are all cancel off. If I'm going to do a reciprocal on all these values over here. So if I'm going to reciprocal it, I will have 1 minus 1 over 3 square of 1 minus 1 over 6 square minus 1 over 9 square, etc. Okay, I hope you see what's going on here. So next, what's going to happen? I'm just going to combine the fractions, combine them. Now I have 3 square minus 1 over 3 square. I have 6 square minus 1, over 6 square, 9 square minus 1 over 9 square. So on and so forth to infinity. Hence, so very simply, what's going to happen now? Basically, I'm applying what is called difference of two squares. So 3 square minus 1, for example, can be rewritten as 3 minus 1 times 3 plus 1. So in this case, you have 2 and 4. So, so this is how I get 2 and 4 here. Likewise, 5 and 7, because of difference of two squares. Likewise, 8 of 10, because of 9 square minus 1. If I'm going to use difference of two squares. Likewise, the denominators are 3 square, 6 square, 9 square, etc. So in this case, I will just put as 3 of 3, 6 of 6, 9 of 9, etc. So if I'm going to do a reciprocal on both sides of the equation, I will have basically my 2 pi over 3 root of 3 as 3 square, 6 square, 9 square, etc. Denominator will be 2, 4, 5, 7, 8, 10. okay, and all the way. So this is, okay, how I prove the next Wallis product, okay, and the next Wallis product is over here. Okay, so using the same technique, now I'm going to do it for x is equals to pi over 4. So for pi over 4, same thing, exactly the same one as what we have just done initially. So in this case will be 4 square minus 1, okay, over 4 square, 8 square minus 1, 12 square minus 1, etc., etc. Okay, because I just basically re-evaluate all my respective terms in the product. Okay, thus on the left hand side, this is equals, okay, to 4 over root 2 of pi, which is hence simplified will be 2 root of 2 over pi. And based on what we have derived earlier, the same technique, okay, using the difference of two squares, thus I have 3 on 5 for 4 square minus 1, 7 of 9 for 8 square minus 1, 11 and 13 for 12 square minus 1. Okay, and denominator is just, okay, their respective multiples of 4 square. Okay, so you can see very straightforward. So hence, I'm going to do a reciprocal on the left-hand side. If I do it right-hand side, I also do a reciprocal. Thus, I form the next Wallis product. Okay, and for the last one is actually using x as pi over 6. So in this case, okay, I will just derive basically the same thing. Okay, nothing special. So far, I'm just basically getting all the respective terms. Same thing, difference of two squares. Hence, I now get the respective products. So the last but not least, okay, you have pi over 3 as multiples of 6 in the numerator. Okay, 5 and 7, 11, 13, 17, and 19, so on and so forth in the denominator. Okay, so in other words, okay, today we actually look at 3 more Wallis products, okay, on top of the 4th one that we talked about in the previous video. And yeah, basically, these are the respective x values of x from the horizontal axis, okay, touching, okay, the curve of sine x over x, okay, and we are getting the respective outcomes, okay, for the functions. So these are the values that are convergent, and they are rather beautiful. Why? Because it actually shows multiples of 6. For example, in this case, multiples of 6. Okay, what else? Okay, so you have multiples of 6, you have multiples of 4, and multiples of 3. Okay, so by looking at these 3 values, we are able to derive another 3 sets of beautiful Wallis product series. Okay, and that's it. Thank you very much for watching. Have a nice day. Goodbye.